All right, welcome, ladies and gentlemen. This is video number 4, the last required video for the Chapter 4 Solution Chemistry and Stoichiometry unit. And this is the video where I'm very specifically going to get into solution stoichiometry, how we can integrate molarity as a new stoichiometry tool in classic stoichiometry problems. And the nice thing about this is that it shouldn't feel crazy different from any other stoichiometry problem. And I want you to focus on the similarities here because there's tons of similarities. So, solution stoichiometry. Just to kind of walk you through sort of an absolutely classic solution stoichiometry problem, what does a solution stoich problem look like? It's really essentially a problem where you would be given information about molarity and volume of compound A or species A, and they'd ask you, based on a chemical equation, based on a chemical reaction, what is the molarity or volume of compound B, species B? So notice that this is phenomenally similar to the idea of going from grams of A to grams of B, a classic mass problem. Only now it's molarity or volume of A to molarity or volume of B. So we're going to follow a very, very similar roadmap. And the idea is that we're going to start by calculating, if you have molarity and volume, again, this combination of two numbers really gets you moles. So let's calculate that. Just like we want to automatically go from grams to moles via GFM, now we automatically want to go from molarity and volume to moles via the molarity definition. Molarity is moles per liter. Once you have moles of something, then we're going to break out our absolutely iconic mole ratio, right? Coefficients, mole ratios, they are your friend. They basically control everything, right? Moles of one thing to moles of something else through the coefficients. So this second step is no different than so many other second steps that you've seen so far. This idea of using the coefficients in the balanced equation to get your mole ratios worked out. Then once you have moles of B, well, then the final step is basically just finishing the problem, doing whatever it asks you to do. Maybe it asks you to calculate volume and it gave you molarity. Well, boom, you can do that. Maybe it asks you to calculate molarity and they gave you volume. Well, you can do that too. Or maybe it asks you for grams. Great, if you have moles of B, you can go to grams of B using the gram formula mass. So this is a very, very similar type of problem to mass. It just uses molarity. Molarity equals moles per liter first. Now, a couple things to consider just in general in stoichiometry. When you do that, always a good idea to kind of break down the information that's in the problem first. If a reaction has not been given to you, oh my God, you write that reaction and you'll make sure it's correct and you'll make sure it's balanced. You need those mole ratios. So, we want to write that balanced equation. Sometimes a net ionic can suffice if we feel comfortable with that, just showing what's actually changing. Then that can work too. Calculate moles of reactants. One way or another, whether it's through molarity and volume or possibly through grams. Always think about limiting reactant. Always, always. We are never not thinking about limiting reactant. It is always on our mind. And we're always going to use that idea to then go forward with the stoichiometry, work out moles, and then, the final step, basically answer what the problem asks you to do. Acid-base titrations. So acid-base equations, right? Acid plus base. In Regents Chem, you learned it makes water and salt. We're going to hone that definition a little bit later on when we do our acid-base unit, because that's a little too broad for my liking. But titration is worth mentioning. Titration is that process. Remember the process with the burettes? The burettes, the really tall, skinny things where you opened it on the bottom and stuff came out into the flask underneath it. Titrations are processes that are used to determine molarity. More often than not, it's used to determine the concentration of something. You don't know what the concentration is of something, you can actually do a titration. And this is something you could do for, like, pond water samples. What's the concentration of dissolved minerals in the pond water samples? Do a titration with the pond water. And it's based on, any titration is actually based on this thing called the equivalence point. How do you know when you stop titrating? You want to stop titrating when you hit this thing called the equivalence point. And the equivalence point is when you have enough titrant added to react exactly with the analyte. Basically, the two things that you're working with, the two compounds, have completely reacted with one another. What does that mean, enough titrant has been added? It means that there is no limiting reactant. It means that you have a perfect stoichiometric ratio between your reactants. That's what the equivalence point is. The reason that is called the equivalence point is because you have stoichiometrically equivalent amounts, which is basically a fancy way of saying there's no limiting reactant, everything is used up, you have a perfect ratio. And if you titrate to the equivalence point where you know that everything is used up, then you can use that information, what volume was required of each thing to get to this equivalence point, this point at which everything got consumed, at which you have the perfect mole ratios between your two reactants. You can then use that information to calculate things like concentration of the unknown. But the thing about the equivalence point is you can't actually see it. I can't look at a beaker full of sodium hydroxide and hydrochloric acid and say, well, obviously the moles of HCl and NaOH are equivalent to one another. I can see that with my eyes. No, you can't. You cannot see that. So frequently we use an indicator. And you want to pick an indicator that has an endpoint, i.e. the point at which it changes color. You want to pick it so that it will change color right around when your equivalence point occurs. Because that way you have a visual cue that you have reached the equivalence point. And so phenolphthalein, that classic hot pink to colorless, or colorless to hot pink indicator in reagents that you use, that we're going to use again, that was a way of indicating that you've hit this equivalence point, this point at which you have stoichiometrically equivalent amounts of stuff. And you can do this with acid-base reactions, and this is how you're going to do acid-base calculations from now on. You're going to use this concept of the equivalence point to sort of prove your point. And no one is ever going to use the dilution formula to prove their point, because that is for diluting things and not for reacting acids and bases. So we're going to end on a problem, on a classic solution stoichiometry problem. I really couldn't have picked anything that I think more better typifies solution stoich than this one. So what is the molarity of an NaOH solution of 48 mils is needed to neutralize 35 mils of a 0.144 molar H2SO4 sulfuric acid solution. First thing you should do, you might be thinking, oh, we've got like molarity and volume, let's calculate moles. My answer is no. The first thing that you need to do, write a reaction. One has not been given to you. That is the first thing you need to do. You must start by writing a balanced chemical equation. Why? Because you need those mole ratios. Those mole ratios are critical, and you do not know what they are if you do not have a balanced chemical equation. If a reaction has not been supplied to you, you write one. So what are the reactants? The reactants are NaOH and H2SO4. What type of reaction is this? Two possible answers. You can tell me it's a neutralization reaction, and I agree, but neutralization is within the broader category of double replacement, which is a little bit better bet for us, thinking of this as a double replacement reaction. So considering this as double replacement and having the compounds switch partners, as it were, the Na is going to combine with the sulfate, and the OH is going to combine with the H. So if H and OH combine, well, that's just HOH, aka H2O, but I like writing it this way as HOH because then I can see a little bit more clearly the double replacement bit. Remember, H2 doesn't mean H2 and H2SO4, it doesn't mean hydrogen gas, it means that you have two H plus ions, so you basically have one of them here. And then I have Na and SO4. Well, Na is +1, SO4 is -2. So when you combine these in a way that balances charge, it's not going to be NaSO4. And that's why you've got to be super careful on these things, because Mrs. Julian is not going to go easy on you and give you everything that's in a 1-to-1 ratio. Oh no, ha 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 ha, oh no. It's going to be, the formula is going to be Na2SO4. Right, Na2SO4, because again, Na is +1, sulfate is -2, so I'm going to need two sodiums to balance out the charge of the sulfate. So I have my reaction, but it's not balanced, so now I have to go in and balance it because I desperately need these mole ratios. So balancing the sodium, because that's probably the clearest place to start, I'm going to need two NaOHs there to balance the two sodiums and the Na2SO4. And then Notice that I have 2 hydrogens here and 2 hydroxides here, but I'm only have 1 water here. So if I put a 2 in front of that, right, 2 OHs, 2 H's, that's going to give me 2 water. So my equation is balanced. Now I can start thinking about the numbers. So I'm going to pull numbers out of the problem. 48 milliliters. That number belongs to what? That number belongs to the NaOH solution. So I'm just going to put it right under the NaOH. I like to organize my numbers like under things in a balanced equation. It helps me kind of see what numbers belong to what. So neutralize 35 mils of 0.144 molar sulfuric acid solution. So the 35 mils and the 0.144 molar belong to the sulfuric acid. What is it asking for? It says what is the molarity of an NaOH solution? So it's asking me for the molarity of that. So now we can start our math, and the question is, where do we start our math? Because we kind of have a lot of numbers. So I'm either basically starting with the sodium hydroxide or the sulfuric acid. I'm going to start my math here with the sulfuric acid for 2 reasons. The bigger reason is that I have more information about the sulfuric acid than I do the NaOH, right? The problem asks me for the molarity of the NaOH, which means that I obviously do not have enough information about the NaOH right now. Clearly, I must figure something out about the NaOH. So I have more info about the sulfuric acid, and hopefully at this point, notice I gave you the magic combination of numbers. I gave you milliliters and I gave you molarity. Volume and molarity together equals moles, right? We can calculate moles if we have this special combination of numbers. So let's start there. Let's get our moles of sulfuric acid, because I have the molarity and the volume of that. So just using the definition of molarity, 0.144 molar x moles of sulfuric acid over 0.0350 liters. I hope that you can convert milliliters to liters in your head. I encourage you to do that. That gives me moles of sulfuric acid, so 0.00504 moles of H2SO4. Cool. I've got moles of sulfuric acid. So what? Problem asks for the molarity of the NaOH. So what are we going to do? We have moles of one thing, and the problem is asking about information for something else. How do we possibly do that? Oh, I don't know. Mole ratios. That's going to be our next big step. Mole ratios, they are your friend. We're going to love them, use them all the time. There is a 1:2 ratio between the sulfuric acid and the sodium hydroxide. So I'm just going to set up a T-chart because I can go from moles of H2SO4 to moles of anything else in this balanced equation. But I'm going to choose the NaOH because the problem asked me about the NaOH. And this right here is why you're going to do this with mole ratios and why you're never, ever going to do this to me with the dilution formula, which is for diluting things and diluting things only. So I'm doing this math. The moles of H2SO4 cancels out. I'm left with moles of NaOH. So I have 0.01008 moles of sodium hydroxide. Cool. Is that what the problem wants? Nope. It wants the molarity of the NaOH. But, hey, look at that. It gave me the volume of the NaOH. And now I have the moles of the NaOH. And I also know the molarity is moles per liter. And, hey, I have both of those things. So I can go 0.01008 moles of sodium hydroxide divided by the 0.048 liters. That is the 48 milliliters. Do that division out, keeping sig figs in mind because everything should have 3 sig figs here. I get 0.210 molar sodium hydroxide. And the big, huge point about this problem is it really isn't that much different than a mass-to-mass problem. To me, there are striking similarities because the second step is identical, right, the mole ratio bit, and the first and third steps are very, very similar to a mass-mass problem because in a mass-mass problem, you're just going from grams to moles and then moles to grams through gram formula mass. This is exactly the same idea. I'm just going from molarity and volume to moles and then from moles, in this case to molarity, through the molarity definition. So very, very similar. Solution stoich is really not that much different than regular stoich.